Welcome back. In today's video we're going to be talking about how to create a component from scratch, and we're also going to add on to that how to take that component and create a breakout board. A lot of times what you want to do when you're prototyping is you have some unique part that doesn't fit in a standard breakout board, so you need to develop your own breakout board so you can first prototype with it and then later use that footprint in a final PCB design. So we're going to be stepping through that entire process start to finish in this video. I'll move kind of fast, or at least as fast as I kind of move, knowing that I'll try to narrate what I'm doing as I'm going along, but knowing that you can pause and rewind along the way. But we are doing it. Some videos sort of don't start from scratch. This one is going to be just start to finish all the way, how to create a breakout board for a unique component using Altium. So the first thing we'll do is we will start up Altium Designer. And the first thing we're doing is we're going to be creating a part. And it's important to understand that with every component, there's basically two halves to each component. There's the schematic side. The schematic side shows logically what signals are connected to what pins, right? What signals are represented by the part, what inputs and outputs the part has. And then there's the footprint side. And the footprint is the physical details of the part. So the physical details of the part, like how big the pins are, how big the footprints need to be, the physical size of the part, the physical orientation of each of those pins. And what the software does is it maps basically the logical pins. Oop, I sort of tested this before I started it up, so it kind of showed where we're going there already. So the software basically connects this sort of logical description of the part in the schematic with the physical definition of the part that's in the footprint, and that connection is done using a pin map. But it's really important for the software, for all automated design software, to have sort of a knowledge of both the physical orientation and the physical composition of the part, as well as the logical orientation and the logical composition of the part. So we have to define both when we're making a new part, and we have to link those two together. And so we'll go through that. So the part that I want to do today, and this is, I don't want to do a lot of, you'll see a lot of tutorials that are just, here's a 8-pin dip package and we're going to make a footprint for it. That's kind of boring. I'm going to talk about what happens when your footprint's a little bit different, how to make a footprint that's got something a little bit weird or wonky about it, maybe something that's a little bit out of the ordinary. So today we're going to do a part that has an uneven pin spacing and a part that has a thermal pad. So both of those things they come up a lot, and it's good to know how to create a new part for something that's a little bit stranger than sort of the standard component. So the first thing we need to have if we're going to create our own part is we have to have a library that holds the PCB definition for that part, and we also have to have a library that holds the schematic definition for that part. So the first thing we're going to do is we're going to create two new schematic libraries and PCB libraries. So we're going to create a library. We're going to create a new schematic library, and then we'll go back to our projects tab, and we will go new library, PCB library, and go back to the projects tab again. And what you can see is now we have these two source documents. We don't actually have a project yet, so these are just sort of floating out there. We just created them. These are by default called, schematic library 1, PCB library 1. We can change these. So let's save these files to a certain location that we know, and let's give them names that are a little more appropriate. So we will let's go into projects. We will go new folder. We'll just create a folder called libraries. And we will save this as senior project. We'll just call it senior project. And then this one as well, we will right click, save as. Senior project. Okay. So now we've got those two files saved in a location that we know. If you are creating a library that's for your senior project, it's good to keep it organized somewhere. Don't have it be within the file for any particular board design, any particular PCB, have it out somewhere in a libraries folder or in the Altium default folder. But just know where you keep it, know where you save it, make sure it's somewhere that gets backed up, make sure it's somewhere that moves with your file. So if you are moving a file and it's relying on that library and it's not going to be able to access it outside, make sure it's got some local reference, make sure there's some way that, yeah, that's a library that you typically use with your parts. So what we're going to do is we're going to first start by, for this part, we're going to first start by looking at the PCB footprint. So we're going to define the hardware side of it, the PCB side of it first. So if you click on, we have our files open. If you click on the PCB project, it just shows a gray screen. One thing that throws a lot of people off is they don't know how to get back to the PCB library definition. So just down here in these little tabs down here, click the PCB library tab, and that's going to take you to sort of the more standard, the tab that just sort of shows the details of this particular library. Now we just created this library, so it has one default component in it. And what we can do though is we can always add new components. Right? We can add multiple components to this library. Same with the schematic. We can add lots of schematics to it. But for right now, we're just doing one. So we're going to delete these. All right, so let's find our part. So let's go to DigiKey. Oh, I typed that wrong. That could have been bad. Ooh. And I don't know why DigiKey's taking us to what looks like their mobile site here. There we go. All right, so I'm going to look for a buck regulator. And I know the one I'm looking for because I've already done this. But we're going to look for a buck regulator that can buck a really high voltage. So we're going to sort through here, and we're going to do... So we're going to take one that can have a massive input voltage. Let's get one that's maybe in stock. And this is the one that's got that nice purple link, which means it's the one I've already looked at here. So this is the part that we're going to make. It's a little nifty. It's a buck regulator, but it's a buck regulator that can handle a really high input voltage and buck it down to a low voltage if you want. So this is the Linear Technologies LTC3638. You'll notice just from looking at the picture, this is kind of a strange footprint, right? It's got a thermal pad on the bottom, and it's got the pins here aren't quite spaced uniformly. So it's going to be something a little bit different for us to work with for this particular example. So the data sheet for this part is everything. This is going to tell us basically everything we need to develop this component. It's always good when you know you're going to work with a component to really read through the data sheet, make sure you understand it. A lot of times there's interesting stuff, for instance, if you're developing a breakout board, you might know that you're always going to have two signals connected to each other no matter what. So maybe you just want to connect them on the breakout board and sort of save yourself some pins. We're not really going to do that. We're going to sort of keep it a little more limited than that. But we're going to have to rely on this data sheet to find the pin information and the footprint information. So if we scroll down, and I'm just mouse wheel scrolling down, we get down to this page. Usually you'll find it about here, right near the end of the data sheet. Maybe not quite till it gets to the packaging definition. Sometimes it'll have sort of a tape and reel definition past this, but usually it's near the end. It's either near the beginning or near the end. And we have our package description that's showing the shape of the actual component, and also it's defining, and I'm going to just control mouse wheel zoom in here, but it's also defining how the pad should be laid out for this particular design. Now note that when we're talking about how the pads are laid out, you can have different pad layouts for high density, low density PCB designs. So what they say is doesn't necessarily have to be this way. You can modify this footprint if you need to for your own purposes. A lot of times what I like to do is, especially if I know I'm prototyping, is I will make the leads on these a little bit longer. Sometimes for high density PCBs, they'll have these really short pads, electrical pads, and it's good for reflow, but it's really tough to get an iron in there if you're trying to do rework, especially with fine pin packages. With fine pitch packages, it's very tough to get a soldering iron there. So sometimes I'll sort of extend out these pads a little bit to make it easier on myself. I'm not going to do that for this one. We'll just follow the actual definition that's here in the data sheet. So looking at this definition here, there's a couple things that are a little bit annoying about this definition. One, it defines the geometry in this direction based on the outer edge of these pins. When we're placing pins, we're usually placing them by the center of the pin. So sometimes it's nice when they have a center-to-center definition for this geometry, but it's fine. I mean, it's just subtraction. It's not that tough. And one thing we'll see here, though, is these pins right here, it basically shows the pitch. This is 0.5 millimeter pitch for these pins. But here we have these sort of 2 pins over here on the edge, and those 2 pins are not 0.5 millimeter. Those are 1 millimeter spaced away from the component. So from each other. So when we're doing this, we're going to have to note that these pins here are 0.5 millimeter spaced, but these ones are 1 millimeter spaced. We also know that the center-to-center distance here, the length of these pins is given here. It's 0.88, or the length of these pads is given here. It's 0.889 millimeters, plus or minus 0.127. Clearly, though, this is, this part was designed sort of using imperial units, so it's really sort of 0.4 inches is the max. Sometimes, whenever we have these tolerances, we have a size and then we have a plus or minus. Especially when it comes to defining the physical geometry of the part, I usually like to use the larger size. The point of doing a 3D body or a physical geometry, which we'll do for this, is to make sure that things don't bump into each other. So if you have a range, if you have a tolerance for the part, and you use the largest possible size that's specified in the data sheet, that's going to guarantee you that if 2 things don't collide, they're not going to actually collide when you finally build your board. And it's not such a big deal for these parts, but when you get to big capacitors and big inductors, things that sort of really stick up off the board and maybe get bigger off the board than they are where they connect, then it becomes really important to make sure that you're using the largest specified geometry within tolerance here. So getting back to the pads, the pad size, the actual dimension of the pads themselves, looks like from this geometry, these are about, we'll call it about 0.3, 0.305 plus or minus 0.308. So for the pads, we'll just do 0.305 width. The length of the pads here is going to be 0.889. So one thing to note is if the length of the pads is 0.889 and the distance end to end is 5.10, we can just, to find the center to center distance, we can just subtract, take 5.10, subtract 0.889, and then we'll get, what is that, 4.211, I think? Yeah, 4.211. Yeah. So, so we'll use that, right? And we'll get to that very soon. So first thing we're going to do is we're going to place all of these pads, and we're going to have to place them sort of knowing this. But knowing that our pitch here is 0.5 millimeters, and our center-to-center pitch here is going to be 0.4211 millimeters, that's going to let us make our lives a lot easier by adjusting the grid in Altium. So we get here, this is our, we have a component. We can leave the name like that for now. We'll change it a little bit later. We can do control mouse wheel and zoom in until we see a grid. I don't actually see a grid here. That's fine. It looks like we are way zoomed out right now. Not fully sure why. But the first thing we want to do is, if we are going to specify the units for this part in millimeters, we want to make sure we're using millimeter units for our grid. It's easy to do that. To do that, all we have to do is press Q. So you press Q, and now you see millimeters up here. Press Q again, now you see mils. Press Q again, millimeters. So we can switch back and forth between millimeters and mils as needed. And again, if you're gonna define something in millimeters, it's best to use millimeter grid spacing, millimeter grid. Just keep everything metric or keep everything imperial, whichever one you're using. And it's quite common to see PCB components that use one or the other. Don't be afraid of mixing and matching the two. Just make sure that if the part is defined using imperial units, that you use an imperial grid for it. Okay, so I usually like to set up my grids when I'm doing these designs, just so that automatically I can just click and place pads exactly where they need to go. So in this case, I'm going to want to set my X grid to 0.5 millimeters, and I'm going to want to set my Y grid to 4.211 millimeters. So to do that, I'm going to press, so I've switched to metric here, I'm going to press the grid the G key. I just pressed the G key. To do it again, press G. Pops up this window. So for snap grid X, I am going to just go to set snap grid, and I'm going to do 0.1 millimeters. And then I'm going to hit the G key again and do snap grid Y. Set snap grid 4.211 millimeters. So now my grids should be, you can kind of, I don't know if that shows up very well. My grid is now, we have the really long grid in the Y dimension and a fairly short grid in the X dimension. And that's just fine for placing pads. So the first thing I'm going to do to place these pads is I'm going to go place pad. And this pops up the last pad size that I use pops up here. So this is a surface mount pad. A lot of times if you're first using Altium, this pad is actually going to be a through-hole pad. So I'll show you how to do that. So to modify the pad, you're going to press tab, and it brings up this pad thing. Now if the pad that was shown was a through-hole, if it was a through-hole, usually if it's a through-hole, that means that it's got, it'll have a specification here of, I don't see it, it's a multi-layer usually. Oh, well, I don't see it. Yeah, but usually it's going to be, for a through-hole pad, it's going to be a multiple layer setting here. To get back to a surface mount pad, just go up to top layer and do it that way. We have a designator for the pad. That's really important. We're going to want to make sure the pad designators match what's shown on the data sheet. And we can set our geometry for the pads right here. So in this case, let's go back because I forgot. So the width of these pads is 0.305. The length of the pads is 0.889. So 0.305, 0.889. And now that looks more like the pads they had on the data sheet. And we will click OK. And now you'll notice this pad is, oops, I think I set my grid a little bit too small. My X grid I think is a little bit too tiny. So I'm going to do grid, snap grid X, set snap grid. Sorry, this should have been 0.5 millimeters. Okay. So now you'll see this pad just automatically snaps to where it needs to be in its spacing, right? So it's very easy now for me to move these pads. These can be pads on one side of the chip, these can be pads on the other side of the chip, and they're automatically going to snap to the proper spacing. So the next thing I care about is the ordering and the numbering, because if we place these pads in order, it's going to keep all the pad numbering and it's going to work out just fantastic. So let's go back to the data sheet. And if you look, we have our pin numbering here. You got to be really careful here, because this is the view of the bottom side of the pad. So it shows pin 1 through 8 through 9 through 16, but that's from the orientation of the bottom. What we care about is the orientation from the top, which here shows pin 1, 2, 3, 4, 5, 6, 7, 8, and then 9, and then back to 16. And also notice they skip pin numberings here. They go 1, skip 3, skip 5. That's really annoying that they did it that way, but what they did is they sort of were copying, they were taking a standard footprint and they were pulling pins out. So they were leaving the pin numberings for the standard footprint, which, I mean, that's the way they chose to do it. We're going to follow that just to be consistent with the data sheet, but it's a little bit strange. So we'll start with pin 1 down here. We'll do a double gap here for these and then continue on in this orientation. So let's go back to Altium. So we are going to, first of all, press tab again. Let's start with designator 1, and we'll place that here. It doesn't really matter where we go. Now the next one, we need to have a double spacing to go from 1 to the next pin. But the problem is the next pin was not pin 2. So Altium is automatically going to increment the pin number. Unfortunately, we want to go 1, 3, 5, 6, 7, 8, 9, 10, 11, 12, 14, 16. It's a weird spacing. So it's fine. We'll just hit tab again and we'll change this to 3. Click. Hit tab again, changes to 5. Click. And now it should automatically be 6, 7, 8, 9, 10, 11, 12. Hit tab again. It should be 14, double spaced. Hit tab again, should be 16, double spaced. Okay, perfect. All right, so we've got ourselves if we zoom in, we can see these pad numberings here. So we now have those outer pads as specified in the data sheet. So let's go back to that data sheet. You'll see another pad here. There's a center pad. That's a thermal pad. So these pads, they're quite common on devices that dissipate a lot of power. Usually the thermal pad is there so that you can connect that thermal pad to other copper that's on your board to sort of give more copper surface area to dissipate heat a little bit better. There's different ways to do the thermal pad. So some people with the thermal pad, they don't treat it like a pin. They just treat it like a chunk of copper that's there on the board, which means that if you don't treat it like a pin, there's no way to make there's no way to define an electrical connection to it in the schematic. Usually I like to treat it as a pad, as an actual pin that has an electrical signal that shows up in the schematic, and that way if people want to tie it to a particular ground plane, they can do it without Altium throwing errors that then have to be ignored. So we're going to just treat it like any other pin, this sort of center pin here, and we'll just call it pin 17. So some people call it pin 0. I kind of don't like using pin 0 necessarily. We'll call it pin 17. Okay, so we'll go back to Altium. Oh, I should have checked the size. So the size of this thermal pad is 2.845 millimeters by 1.651. So 2.845, 1.651. I'll definitely forget that, but we'll go. So we're just going to place a new pad. Oops. And then we'll hit tab. And this guy, designator 17. The X side, and I forgot it already. I told you I was going to do it. 2.845, 2.845, and then 1.651. Okay. So now you'll notice, right? We can't place this pad where it needs to go because our grid spacing is really coarse. So there's a couple things we can do. This pad needs to be just dead center in the middle of this chip. And the problem is sometimes dead center when we have pads with weird spacing is a little bit hard to get to. But there's a trick if you want to get to the dead center middle of the chip. And that is I'm going to drop this pad down somewhere. And then I am going to just delete it. I'm going to control exit. And Altium wants me to say, before I cut this thing, it wants to say where the sort of center of motion of this thing should be, so I'm going to just choose it. So what I can do is to find the center of this, I can actually just move the midpoint of our grid here. So I can move the center point of the grid to the middle of this footprint, and to do that I can go move, set reference center. So that actually set the 0 reference. If I click here and I look up here in the at the x and y coordinates at the center, that is now 0, 0. So this is going to be negative, negative, positive, positive, and so on, right? And the cool thing about this now being the center of my grid is, regardless of what my x and y grid snap was, when I control V this thing, it can snap right to that center. So that's a nice little way to cheat and get a center. So now these pins are all here. Usually after I get my pins aligned and everything's there and my center is the center, or my origin is set to the center of the object, I'll usually go back to a more reasonable grid spacing. So I'm going to press the G key, and then I'll go back to like 0.1 millimeters or so for my grid spacing. So there's a couple other things. We have the physical components now down. So everything that's listed here is done. But there's a lot of stuff we like to add to this footprint while we can. So one thing we like to add is we like to add silkscreen that helps us, once we actually have this part on a board, it helps us determine the orientation. So right now, if I looked at this, I wouldn't know which orientation to place my chip. I wouldn't know where pin 1 is just based on this footprint right now. So what I like to do is I like to put a pin 1 indicator. Usually a pin 1 indicator is done by a dot, and there will be, a dot impression or a dot, laser marking on the actual component, and then we'll also have a silkscreen dot on the board. It makes it very easy to place parts. Sometimes I also like to just put an outline of the part so that when I have my PCB and there's no parts yet on the PCB, I can still sort of generally see where those parts connect, especially for a high density board. Sometimes just looking at it can be tough to see where those center bodies of components are. So I'll kind of do both just sort of for fun here. So let's go back to this. So let's put a little silk screen that shows the outline and a silk screen that does pin 1. So the size of the body of this chip is 3 by 4. So it's 3 millimeters by 4 millimeters, and it's centered right here. There's what I can do is I can switch to top overlay. That's going to be that silk screen that goes over the top of the board, and I'm just going to place a line. And so I'm going to do the outline of the board first. Sometimes it's good to just do it, if I know I have to have a 4 by 3 millimeter outline, just do it over here and change my grid. You know what, actually we can just do it directly. So if my grid is nice coarse 0.5 millimeter, so a 3 by 5 is going to be, that's getting a little close to the pad, so I might kind of move it in. Might move it in a little bit, but so it looks like we got 2 millimeters here, 2 millimeters here. So the outline of our physical chip is going to be around here. I don't want to get my silk screen that close to this solder mask though, so I'll probably set my grid a little bit finer. 0.25 like that, yeah. And now we'll do the outline like this. So it's not totally correct. Oops. It's not totally correct because actually the board comes out a little bit further. It comes out to here. But I didn't want to get that silk screen that close, so it's close enough. But you can see at least where the body of the part is. Now we have to add a pin 1 indicator. So pin 1, if I look at the data sheet, pin 1 is right here. So the marking on the part is going to be here. Pin 1 is going to be here. I'm going to also put a dot here. Sometimes you'll put the dot inside here. There's not really a good space for a dot though, so I'm just going to place it here. Now you'll notice if you try to place a dot just with a line, it doesn't really let you do it. So what you can do is just make a line that's a little bit longer. I'm gonna just zoom in, and you can just shrink it down to a single line with the same start and end point. You can also do, there's lots of other ways to do it. You can also place a circle, place a full circle and just shrink it down to the point where it makes a dot. There's lots of ways to make a dot. Okay, so I got my pin 1 indicator. Where you put that also, it's kind of up to you. Some people maybe would put it a little bit further out like this. It doesn't really matter, except that sometimes this can get in the way of other components. So if something else is going to be here, maybe that's a little bit too far away. I'm not too worried about it though. Oops. We'll do it right there. Okay. So the next thing I'm going to do is a 3D body. So quite often it's useful to have a 3D body for a part. The biggest reason to have 3D bodies is it's not just so you have a nice pretty picture that looks like what your final board is going to look like. 3D bodies are important to make sure you have geometric clearance of parts. So the parts as they're shown as a footprint don't necessarily represent the full three-dimensional geometry taken up by those parts. Sometimes something will have a tiny footprint, but when it comes off the surface of the board it gets really big. So capacitors do that all the time. Inductors sometimes do that. And so we want to make sure, sometimes you'll have one board stacked on the other. So you want to make sure we have geometric clearance. We want to make sure we don't have any steric hindrances. I think that's what chemists use to say when two molecules don't physically fit together. It's a steric hindrance. So I don't know, it seems like it'll work for PCB stuff too. So we're going to sort of generate a 3D model that sits on top of this that's going to show up when we actually view this thing in the 3D view. Let's actually, just for right now, take a look at the 3D view of this thing. So let's take a peek here at the 3D view. It looks pretty good, right? We can sort of see that silk screen. We can see those copper parts. Of particular note here, this copper is nice and exposed. So this copper is exposed. There's no solder mask covering it up or anything like that. So and I press the 3 key to get to the 3D view. I press the 2 key to get back to the two-dimensional view here. Okay, so let's create a 3D body here. So first of all, let's go back, and I think we already saw it. We saw that our that the body of this chip is going to be 4 millimeters by 3 millimeters. Let's go back and see. So we have 4 millimeters by 3 millimeters, but the thickness of that is 0.86 millimeters, and it's offset 0.1 millimeters from the surface. So it's sort of floating a little bit here. So that's easy enough for us to do. So what we're going to do is we're going to do place 3D body, and so we will change the color of this guy to kind of a dark gray. I guess it's sort of the standard dark gray that's used. So this is the 3D body view. So there's lots of ways to put 3D objects. You can do a generic 3D model. That is going to be if you wanted to really build a detailed part and you wanted to go into like SolidWorks or something and build a nice 3D model and give it all sorts of colors and give it sort of nice silk screened images and things on the top of it. You can go with a generic 3D model and you can import it. Any step file you can import as a part. A lot of times, this is critical too, a lot of times the manufacturers will provide 3D models for all of their components. So sometimes you can just steal the 3D model from the manufacturer. It's really easy to just do that and just move it into the right orientation. We're going to make one though from scratch, and we're just going to do a simple one. There's not a lot of, we don't have to define a lot of complex geometry to sort of get the gist of where this thing goes. So we know the standoff height was 0.1 millimeters for this guy. And it was 0.1 millimeters, and then it was, I think, the thickness of it was 0.9 millimeters or so. So the overall height of this guy is going to be about 1 millimeter, right? 1.1 plus 0.86, we'll call it 0.1. And again, that's sometimes where this, where the tolerance comes in. They don't really specify the tolerance for the height here, but they do for this. So we kind of want to use just the largest geometry we can. So about 1 millimeter is going to be good enough. Overall height 1 millimeter. So now it's going to ask us to basically, this is an extruded 3D body. So basically we defined the z-axis in the menu we just had open. Now we are going to define the x and y geometry of this. So we are going to, I usually like to place it off the part, right? The first thing I'm doing is I'm trying to find the geometry, so I'm going to just be looking at these x, y, and dx and dy coordinates up here, and I'll just place it somewhere off the side of the part. So I want this thing to be, I want it to be 4 millimeters wide, so I'm going to just move this until I see that dx go to 4 millimeters. I'm going to move it up until I see the dy go to 3 millimeters. Now I'm going to move it over until we get back to -4, and then I'm going to hit escape to close the polygon. And this is the last. I don't want to do another one of these. So, and now we can move this guy into position. So again, because we had the center was the center of the chip. It's very easy to put the center of this body in there. Let's take a peek before we get any further. Let's take a peek. So I'm going to hit the 3 key, and I'm going to just Control right click to zoom in and out. Shift right click to rotate this guy. So looking at this, that looks pretty good. That looks about like what we're looking for here. And again, this is a way to also confirm that silk screen. So we had that silk screen around there to show sort of the general geometry when we don't have a chip on there. And yeah, it matches pretty well. It's pretty good. So some people would leave it just as this. We can add a little more detail. We can add pins in here a little bit. We're not going to do super detailed pins. I'm going to hit the 2 key to go back and realign myself here. So these pins, you know, there's, of course, they have a very good specification for the pin here, right? You know, they sort of show the angle of the pin here. We don't really care about all that. It's not like we're going to have something snaked in through the side here or over here. So really what we're just going to do is we're going to treat this pin just like a block and just represent it on the image like a block, and that should be just fine. So let's sort of find the general pin geometry. So it looks like the pins are, trying to see where they specify a pin here. So here it looks like the width of the pins are 0.17 millimeters to 0.27 millimeters. So we're going to use 0.27, just assuming they're largest possible size. And the length of these pins, having a little trouble seeing specification for the length of the pins. Well, actually, here's how to do it, right? We know the pin to pin is 4.9 and the body is 3, which means each of these pins' length has to be 0.95. So the length is 0.95, the width is, we're going to do 0.27, and the height, it looks like this guy's a little bit above midway, so it doesn't actually specify it, so maybe we'll just say about 0.6 millimeters sounds about good for that guy. So 0.27 width, 0.95 length. So we'll place another 3D body. We'll change the color to be a little bit lighter. These are pins, so they can be a little bit lighter. And where's a little bit lighter gray? Just a little bit lighter gray. So the overall height, these don't quite go up to the top of the chip, so we're going to change the overall height to 0.6 millimeters. The standoff height is going to be 0 for these guys, because these actually touch the touch the surface of the board. And then again, I'm gonna do the pin off the side. I need a little bit more resolution now though to draw this pin, so I'm going to change my grid to a resolution of 0.025 millimeter. Maybe zoom in here. So 0.27 width, 0.95 length. So again, same as we did before, just looking up at that top left corner until we get to perfect, 0.275. Oops, I messed that up. We can always hit the backspace key to undo that last move. And make sure, so yeah. So we're going to go up now 0.95. And over. Oh, it looks like I made this guy a little bit wrong, so that's alright, we'll fix it. And then hit escape. And then it pops that up, and I'm just going to cancel it. So I actually made this guy a little bit too narrow, so I'm going to click. And I don't want to click on this guy, or it's going to break that. So I'm just going to click off to the side. Make this guy a little bit wider. And we can always check the width. We can click here and move here, and yeah, 0.275 millimeters wide. So this is the part that I want. This is what I need. Now what I need to do is, I zoom out so I can see where I'm going. There, we got way away here. So now I'm just gonna copy paste this guy. So I'm gonna Control copy. Altium wants me to tell it when I copy something or cut something, it wants to say, before you make this go away, what reference on this part do you want to be sort of where you're grabbing it from when you place it later on? So I'm going to just click the center here. And we'll move this guy into place. So just centered on the pin. That's okay. We got a little bit of, we could fix this so it was a perfect match with the grid spacing or with snapping, but you know, I'm not going to bother with it. That looks good enough to me. Oops, I already copied that. So I'm just going to do Control V to paste a new one. I don't know what I did here. Oh, I'll just do Control C, Control V, and Control C. Choose the center. Control V. Control V. Control V. So, and again, I am not putting a lot of effort into this. Your design, you might want to, you know, make it a little fancier. Maybe get on some 3D software and really get a slick-looking part. For this demo, I'm kind of phoning it in here, just sort of showing the basics. You can always put more time and effort into making these things a little bit more precise. Okay, now probably before I placed all those, I probably should have taken a look at one of them in case something was messed up. But to look at this, we'll go back to the 3D view by hitting the 3 key, and yeah, that looks pretty good. So now we have where our feet of this part are is all shown here. So if there were a clearance issue, if something were bumping into that, we would know it based on that 3D view. And that's good enough It's very basic, but still good enough for our purposes here. So hit the 2 key to go back. We can save this, but what I'd like to do before is change the name of this. So this is a footprint. This footprint is not necessarily specific to any individual part. But what we're going to do is we are going to give it. So we're going to give it a name that corresponds to the footprint, not necessarily to the specific part. So if we go back and see what they call it MSE package variation MSE 1612 in parentheses. 16 lead plastic MSOP with 4 pins removed, exposed iPad. Okay. So maybe we'll just call it MSE 16 brackets 12 or MSE 16 mod 12. And so again, just to get to this component definition, I double click the PCB component or I hit tab while it was selected. MSE 16, 4 pins removed, thermal pad. And so this way, let's say I have another part from the same company. I don't want this particular regulator, but the other regulator I do want use the same footprint. I can recycle this. I don't have to redo this footprint for my next part. Okay, so I always like to double check before I leave from doing a PCB part design. I like to check that my orientation, right, where I have the center of this thing, the origin of this thing is somewhere reasonable. It's reasonable to have the origin at pin 1. A lot of people prefer that. Or here, if your origin is way off to the side, when you place this part in, when you add this part to a PCB design, the part is going to be way off in the middle of nowhere. So you want to make sure, you got to be really careful with origins. Make sure the origin in your PCB component and your schematic component is somewhere reasonable, so you don't have these parts that are sort of floating off in the middle of nowhere when you're trying to do your design. Okay, so this all looks pretty good to me. So we're going to save. And now we're going to go back to the projects here, and we're going to look at the so we're going to click on the schematic library that we had created here, and we're going to click on the schematic library tab. And again, we just created the schematic library. It's sort of a bare library. We have one component called component 1. We can add as many components to the schematic library as we want. Let's make this component 1, though, the part that we're actually working with. So let's go back to, so this was the LTC 3638. So we might as well call this guy LTC 3638. And let's also call the symbol reference LTC 3638. Now, what is this default designator? The designator is the label that we use for this when it's actually being annotated on our schematic and on our PCB. So this is the what we want it labeled, right? There's standard there's IEEE standards, and you can find, and we have one if you're at Western. We have one in our library. There's a listing of IEEE standard designators for components. So typically, if it's a semiconductor component, it's going to be, I mean, if it's a CMOS type semiconductor component, it's going to have a designator U, question mark. So if it's if it's an integrated circuit, sorry, I should say if it's an integrated circuit, it'll have a designator U. And then for the numbering, we don't want, the numbering should be defined by whoever is using this part, so we're going to add a question mark to say that question mark should ultimately be replaced by component numbering, so U question mark here. And the description will say LTC 3638 150 volt buck regulator. And okay. So there's a lot of stuff we're going to add to this. There's a lot of things we don't want to forget. If we do a good job sort of building our schematic, our component, it's going to save us a lot of time and effort later on. And there's a lot of neat things we can add to the component. So the first thing we're going to do, I changed the resolution on my screen, so I don't have a lot of space in here. But that's fine. So the first thing we're going to do is, I like to make sure my grid is set to 10. My grid is set to 10. If it were not, I could press the G key, toggle the G key to change our grid sizing. I'm going to keep it at 10. First thing I'm going to do is I'm going to start placing pins here. So pin number 1.
Oh, I'm sorry.
It's all right.
I forgot to count the cables.
So pin number 1, if we go back and if we look up to our,
They all come with one, but they're pretty short.
These do?
Yeah.
Oh, they were. Okay.
we scroll up to our data sheet.
They all come with these. They're short, but if they don't like it, they can get one.
This is probably not the best way to do it. Yeah. So we have our pins labeled here. So we have our pins. They have an actual pin. This is the physical pin numbering. So this is physical pin 1, 3, 5, 6, 7, 8, etc. And then we have our sort of logical description of what signal is connected to each one of these pins. So pin 1 should be the switch pin, and that's what goes to the inductor typically. Pin 3, VN, pin 5, FBO, and so on. So we're going to create a bunch of pins and label them according to this logical description of the pins on the component. So pin 1, we're going to hit, when we selected pin, we're going to hit tab. So we want this guy to be switch, and the designator, that was 1, correct? Yeah, 1. And we're going to click OK. And we're going to place this guy. I want to make sure I stay somewhere near the origin here. It's really easy to get off the rails with these guys. Oh boy. So pin 1, switch, there-ish. Pin 2, and it's going to auto-increment. The problem is there is no pin 2. It's pin 3, it's VN. And of course when I tabbed over, Altium kept following my mouse. So pin 2 should be VN, and it should actually be pin 3. So pin 3, VN. So pin 5 is FBO. Now pin 6 is going to be VPERG2. So I know a lot of people magic at television these parts, but I really want to go through the whole process for everybody so I don't skip steps here. Pin 7 is VPROG1, and you'll notice Altium auto-incremented for us the 2 to a 3, but we're going to take it back to a 1. Pin 7. And the last pin on that side is ground. Now we're going to press the space bar to rotate those pins, because we want the wording to be on the inside of the component and the pins to be sticking out on the outside. Pin 9 was VFB. VFB. Pin 10 is SS.
Thank you.
You back?
244, obviously.
All right.
Pin 11 is ISET.
Hey, what's the first lab in that class?
A week from today.
Oh, what is it?
Pin 12 is OVLO.
Basically checking out the boards and just going over the environment, policies, stuff like that.
Pin 14 is run, so we're going to have to change this to run and change it to 14. And pin 16 is ground. I don't. I'm doing a video right now. Maybe. Well, I got a meeting in 25 minutes, but maybe at 1 o'clock. Okay. Pin. That was pin 16 here.
I wanted to add some code to test the push buttons too and stuff, but I was like, I got the.
Okay, so now we got another thing here. So they show it on the schematic. They show that big center ground plane is pin 17. We actually also made it pin 17. So this is where it's some people don't have a actual pin that you can connect to on the schematic. I like to have a pin that you can connect to for the ground plane, just in case you want to just make it simple on yourself and connect it to ground, and then not have to deal with sort of discarding sort of error warnings that Altium throws. So let's add a 17th pin, and we can do sometimes we can do weird stuff with it. You know, we could do it even like this. You know, this is not that ideal. You know what? Let's not be ridiculous. Let's put it here. And I'm actually going to change the name of this probably to pad ground, just to show a distinction, because a lot of times, you know, you got to make a thermal connection, not necessarily an electrical connection. So sometimes it's good to specify that's not necessarily just an electrical ground, that's a pad ground. So now we've got our pins all placed here. Now to make this thing beautiful, we have to actually put it in a box for a schematic. So we're going to place a rectangle and put it around this part. And what happened? All my text went away. The text went away because this box I just put is over the text. So I just need to move it. So I can go Edit, Move, Send to Back, and then click that box, and it's going to just put it behind all the text then. It's going to make it look really nice. So now this looks like the way a schematic should look. This looks the way a schematic part should look. One thing I'm going to do is I'm going to move this guy a little bit more towards the origin here. There we go. So I'm going to move it just centered on the origin, and again, that's if we're using this part and we're placing this component in a schematic, where the origin is relative to the part is going to determine where the part is relative to our mouse cursor. So we don't want to have the part floating off in the middle of nowhere away from our mouse cursor. Okay, so we've got our footprint defined. Now there's some other details we can add to this. So one thing is really nice is to link this component that we've made to a supplier. That way Altium can give us information like how much it costs, where the price breaks are. It can help us build a bill of materials and things like that. So what I'm going to do is I'm going to go down here and click Add Supplier. And I already had the name in here, LTC3630, and we can search for that. And it's going to pop up a bunch of different suppliers. I use DigiKey to find it. I kind of usually most of my orders are DigiKey, so I'll use the DigiKey version of the part. And then we'll click OK. And what that's going to do is it's going to add some details that were provided by DigiKey to this part definition. So if I double click that, you see it added this supplier, DigiKey, part number, etc. We can also here add whatever parameters we want. Sometimes DigiKey will have a lot of details here that will be added to the definition. Some of it will be visible, so you might not want to have that be visible, so you might want to unclick the visibility. But we can also add whatever details we want to make this more useful for people. So if we wanted to add something like name input voltage max or something like that, and we could say 150 V. Right. So we can add extra details to this, whatever's useful for us. The reason I like this is because it could handle 150 volt input voltage. So that's the little detail I'm going to add. Really, if you're working for a company, if this is an enterprise situation, you want to add a lot of detail to this. And a lot of it can be just taken directly from DigiKey for this information. I would double check though. Always double check DigiKey's what DigiKey says about something and what it actually says in the data sheet, because sometimes somebody finds, you know, a bandwidth equals 2 megahertz in a data sheet, and they say, oh, okay, the bandwidth for this is 2 megahertz, but really the data sheet was talking about something else. So make sure to double check. If there's something critical about a component, make sure to double check it on the data sheet itself. Okay, so that's linking it to a component and adding extra details. There's another thing that's critical, and that is we need to connect these logical pins to the physical pins. And we need to connect this. Right now, this schematic part has no idea what footprint it should be using. So we're going to have to link that. So we're going to click this add down here, add a footprint. And so if I browse libraries here, unfortunately, I don't have my library listed right now. I don't think so. So what I'm going to do is I am going to install a library from File. So this is, I don't want to use the Google Drive version. I want to use the Documents. So it's Documents, Altium Projects, and then it is Libraries, and it's both of these. So we're going to add, these are the ones that we just created. So now we should be able to see these, and I know it's a little confusing here because I already did this and I moved stuff around. Okay, this is the one we want though. This is the one we want. This is the one I just created. So we're going to click OK. And so we're going to, this is choosing this 3D model to link to this component. Or sorry, it's choosing this footprint to link to this component, including the 3D model. We can also do the pin map. We can double check this. Now we made it easy on ourselves, and our pin numbers on the schematic were the same as the pin numbers on the footprint. That is not always going to be the case. So sometimes, for some reason, a manufacturer will use a footprint and the pin numbering that they have is a little bit different. It makes no sense, but sometimes it happens. So you're going to want to check and make sure that the pin mapping is correct. And that basically means that, you know, pin 1 is this switch pin, which has to connect to that inductor. That switch pin, if it needs to be physically connected to the pin number 1 on the footprint, then it needs to be mapped 1-to-1, right? And we could have called this whatever we wanted. We could have called this 7,000, in which case we just would have had 7,000 mapped to 1 over here, and it would have worked out okay. So, but that's silly to do. Okay, so that is the basics of creating a component, creating a footprint, linking the component to the footprint, adding supplier information to the component, adding descriptions to the component. So what we could do now is we can just save this and go back to our projects, and now we have a PCB library and a schematic library with our part in it that we just created. And it's been a little bit too long for this video now, so I'm just going to stop it here, and the next video I'll have will be creating a breakout board with this part and sort of showing how to use this part to create a breakout board. So thank you for watching.